to talk a little bit about the electromagnetic spectrum and how those different kinds of light interact with Earth's atmosphere, and then what the implications of that are for different kinds of telescopes to make different sorts of astronomical observations. So I'm going to talk about this figure. The drawing below illustrates the amount that different wavelengths of light are able to penetrate down through Earth's atmosphere. The shaded regions are used in the drawings to depict different layers in the Earth's atmosphere. Notice that the atmosphere can be completely transparent to light at some wavelengths, so all three lines passing through the atmosphere to the surface of the Earth, and yet can also completely absorb other wavelengths of light, so all three lines stopping the atmosphere before reaching Earth's surface. So there's some that make it all the way to the ground, some that make it just partially to the surface, and some kinds of light, parts of the electromagnetic spectrum, are absorbed in the atmosphere, never reach the surface of the planet Earth. So we're going to go through some questions, and then we're going to play proposal review board. All right, questions first. Which, if any, of the different wavelengths of light, so electromagnetic radiation, shown in the image on the previous page are able to completely penetrate Earth's atmosphere and reach the surface? So we have two of those windows. Visible light all makes it through, the atmosphere is transparent, and the atmosphere is transparent to radio. Which, if any, of the different wavelengths of light, electromagnetic radiation, shown in the image on the previous page only partially penetrate Earth's atmosphere and reach the surface? So ultraviolet light partly makes it to the surface, infrared light partly makes it at least to tall parts of the surface, like mountaintops. So that's UV and infrared, IR. Which, if any, of the different wavelengths of light, electromagnetic radiation shown in the image on the previous page are completely absorbed in Earth's atmosphere, never reach the surface? So this is good for life on Earth. The highly ionizing kinds of radiation, X-rays and gamma rays, are both stopped by Earth's atmosphere and will not make it to the surface. So gamma rays and X-rays. All right, so now we're going to do the proposal game. Federal funding agencies must form committees to decide which telescope projects will receive funds for construction. When deciding which projects will be funded, the committees must consider that certain wavelengths of light are blocked from reaching Earth's surface by the atmosphere. Must consider how efficiently telescopes work at different wavelengths, and also must consider that telescopes in space are much more expensive to construct than Earth-based telescopes. Use these three review criteria when you consider each pairing of telescope proposals listed below, A through D. State which proposal out of the pair you would choose to fund. Explain the reasoning behind your decision for each pair. All right, so let's do the first case. So we have two proposals. Which of the two proposals described below would you choose to fund? Project Delta is a gamma ray wavelength telescope located in Antarctica, which will be used to look for evidence to indicate the presence of a black hole. Project Theta, a visible wavelength telescope located on a university campus, which will be used in the search for planets outside the solar system. Let's make our review notes. So Project Delta cannot work. That is impossible because gamma rays do not make it to the surface of the Earth. So if you make a gamma ray telescope in Antarctica, you're going to see nothing. All right, Project Theta, not only is that possible, so it's on the ground, it's not a space telescope, visible light, it's very efficient. This is actually not only possible, this is done quite frequently, detecting planets by the transit method. So we're going to select theta. Okay, and I'll even say it is an efficient use to find extrasolar planets. All right, let's try the next pair of proposals. And we have Project Beta versus Project Alpha. So Project Beta is going to be an X-ray wavelength telescope located near the North Pole, so went to the other side of the Earth, which will be used to examine the Sun. The Sun is an interesting thing to look at, and active regions on the Sun are prominent in X-rays. Project Alpha, an infrared wavelength telescope placed on a satellite in orbit around Earth, which will be used to view supernovae. Okay, so I think we pretty much have got to throw out Project Beta, because from the ground, again, you're going to detect nothing. X-rays do not penetrate through Earth's atmosphere, so you can't observe from anywhere on the surface of the Earth if you want to look at X-rays. So alpha is possible. I would also note that's going to be pretty expensive, and it's only looking for supernovae, which supernovae are awesome, but that is fairly specialized. But considering I'm pairing it against something that's impossible, that would be the one that I pick. All right, Project Rho and Project Sigma. Project Rho is a UV wavelength telescope placed high atop Mauna Kea in Hawaii at 14 kilometers above sea level, which will be used to look at distant galaxies. Project Sigma, a visible wavelength telescope placed on a satellite in orbit around Earth, which will be used to observe a pair of binary stars located in the constellation of Ursa Major. So let's make some quick review notes for Sigma and Rho. So Project Sigma, so it's a visible, it's going to be on a satellite, it's going to be orbit around Earth, but it's only going to look at a single pair of binary stars. That is outlandish. So Project Sigma is possible, but very expensive and specialized. Okay, Project Rho, you're going to miss a lot of the ultraviolet light, but it is at least possible. Those two, I would actually give it to Rho. So not all of the UV light is going to penetrate through the atmosphere. You can get some of UV light that's close to visible, but the rest is going to be absorbed. The fact that you're on Mauna Kea is going to help a bit, but a lot of the absorption of ultraviolet light is actually happening in the upper atmosphere, and Mauna Kea doesn't really help with that. All right, last pair, Project Zeta, Project Epsilon. Project Zeta, a radio wave telescope placed on the floor of the Mojave Desert, which will be used to detect potential communications from distant civilizations outside our solar system. So this is basically Project SETI, Search for Extraterrestrial Intelligence. Project Epsilon, an infrared wavelength telescope located in the high elevation mountains of Chile, which will be used to view newly forming stars, protostars, in the Orion Nebula. Okay, so this is high elevation infrared light. You will at least get some infrared light to observe, especially when there's a little water vapor in the atmosphere. And then radio telescope, in terms of interaction with the atmosphere is transparent to radio waves. So there's no like showstoppers. This one is more question of opinion. So for zeta and for project epsilon, I can see a few different directions that people want to go with this, but I'm just going to make note that both of these are possible. If I'm only going to look at protostars in the Orion Nebula, that is a little specialized. There are lots of other star-forming regions. Some people, and in fact Congress, has objected to this before. There's actually policy in place to prevent federal funding to look for extraterrestrial life. So SETI efforts are privately funded, not with government funding. Possible, so like possible in the sense of feasible, but I would say this one is pretty hypothetical. Between the two, that's a hard call. My heart is sort of into Project Zeta because that's going to be more interesting than finding out there's life elsewhere in the universe. But I'll follow our congressional guidance. Purpose of this exercise, I'll go along with what is essentially already in existence in the Atacama Desert. Where you're getting fantastic views of protoplanetary disks that are forming stars. So there we go. Some practice at proposal review panels, taking into account what we know about how light interacts with the atmosphere.